Hello everyone, welcome back to another multivariable calculus video. And in this video, I will be talking about the difference between the two-dimensional gradient. So, fx, fy, and the 3D gradient. So, fx, fy, and of course fz. So the difference between them is pretty massive, and it mainly comes from the idea that the two-dimensional gradient tells you that you have to move in its direction to go along a surface, or it's the fastest rate of increase for any given point on a surface. So if you are on like this hill kind of thing and it was going upwards, right, and you're standing here, you would have to go in the direction of the gradient along the surface to increase your z. So that is the 2D gradient. And then for the 3D gradient, it actually tells you the normal vector to some sort of surface. Let's say you had a sphere or a hemisphere, it really doesn't matter. Okay, I'm not good at drawing. This is going to be very tedious. Alright, good enough. So, let's say you're on this point here. The gradient would tell you to go away from the surface and go that way. So students often get confused by this, and maybe even after they take the course, they still don't understand why this is the case. And of course, they'll end up getting a very mediocre understanding of this deeply important concept. So here I will be rectifying that. Alright, so why is it that the 2D gradient tells you something about the tangent while the 3D gradient tells you about the normal of a surface? So let's go back to what the 2D gradient actually is. We'll start there. So actually, we don't have to delete that. We can just like move it up here. Alright. And that goes over there. Alright. So let's use this space over here. Alright. So for the 2D gradient, you're basically having f of xy is, some function of x and y, I don't know, like x squared plus y squared, something like that. Maybe square root it to make it a kind of a hemisphere. So this function, its value is equal to z. Let's erase this portion. Alright. So its output is equal to z. We can imagine it that way. That's how you would visualize it. For this function, z as an axis kind of only exists for the purpose of mapping out the output. There are no z values that are not on this particular function's, you could call it a surface, even though it's not really a surface. But basically, what you would have is this hemisphere here, and ignoring this normal vector here, to increase in z, or to increase in the output f, you need to change in x and y. And the only way to increase in z is by following the surface. Because you're not allowed to go off of the surface like that if you were on this point, you would have to follow the surface in the steepest direction, correct? Knowing that z as an axis is kind of only imaginarily there for the purpose of showing how high the output is. So there's really no point in trying to increase in any other direction, because the main goal here of the gradient is to tell you how you're going to change in z when you move in x or y. And it can only follow the function surface. Alright, now that we have that cleared up, we know why. We know why we have to follow the tangent of the surface, which is, to summarize again, there are no z values off of the surface, so the only way to increase in z for this function is to walk along the surface of the function, or follow it up the steepest way using movement in x and y to define the change in the output. Alright, so we're done with that. Alright, let's I can draw it again. Alright. So now let's go to the 3D gradient. Why is it that it gives you like the normal to a surface rather than telling you the tangent? Well, earlier we saw that the output of x and y, or the output of the function of x and y, is equal to z. That's how we defined z. But here, z is not necessarily a function of x and y, correct? Because we now have a function of x, y, and z is equal to something. So for the example of that hemisphere we had, we would have to draw it as a full sphere. Let's say it were equal to x squared plus y squared plus z squared. Now, this is the function here, and this is the output. The output is the sum of all of these squares. So, it's not the same thing as above, where z was a function of x and y, so we're trying to maximize z when we go along the gradient. Here, we have to maximize x squared plus y squared plus z squared instead of just z. If we wanted to maximize z, well, why don't we just, go up there or something? Assuming that were the z direction. All right. So now allow me to kind of draw an image to demonstrate this concept of maximizing the function here instead of the old function which represented z as the output, or in which z represented the output. Alright, so let's draw a sphere here, or a ball, I don't know. This will take a while, guys. Alright, so good enough. You are standing right here, that's you. Alright, there you are. And, this is like North America or something. I don't know how to draw that. Let's see. You have Alaska, and then, go down like that to Mexico. Alright, there you are in North America somewhere. Okay. And we can draw Canada here, some like islands or whatever. Alright, so here is the North Pole. And there's the South Pole. Let me label those. Alright, so if you were to take increasing your position as increasing in your latitude, so going up these lines of latitude, if you were to take that as increasing your function value, well then you'd probably use a function of x and y to represent z. And here we would just have this. So you would have some function of x and y is equal to z, and you want to maximize the change in z with every step in x and y. So to do that, you'd probably walk along the Earth, kind of like that. And your feet, taking that as your main position, they would also get closer to the North Pole, thus increasing your so-called position, or z value, or the output of the function. However, we have defined the Earth, because it's a sphere, as a function of x, y, and z, namely x squared plus y squared plus z squared. Also, that's the first time I've ever said namely, I think. So you can tell I'm really becoming kind of a math teacher. I don't know. Alright. So, what was it? Okay, so we define our position as a function of x squared plus, as a function of x, y, and z. So, if we want to increase this function, we would probably have to get away from the Earth, right? Because we're currently on it, and a larger sphere would represent the surface drawn by larger x values, y values, and z values. A larger sphere, I repeat, would be the result of having a greater value for the function. Because let's say you had x squared plus y squared plus z squared equals 1. So in this case, these are all limited to a range of, -1 to 1. However, if we were to change that to a number like, say, 100, then any of these could range from -10 to 10, which in a sense is really increasing our function value. So if we wanted to increase this value, we would have to increase all of these ideally. So taking this as a function or as an output, we want to make it as big as possible through increasing all of these as much as we can, or increasing all of this together as much as possible. And to do that, we must go away from the Earth, or from our position here, away from the Earth. So I hope that makes sense. Now, this relates back to why the 3D gradient is normal to the surface rather than tangent to it. Because unlike trying to increase our z value by going along the Earth, let me draw that in red. Instead of trying to go along the Earth to the North Pole, we're instead trying to kind of escape the Earth by moving above into the atmosphere, or wherever we're going. We want to go away from the current level that we're on, or the current surface. So that would bring about an increase in the value of f, the output. And that is the main goal of the 3D gradient. While the 2D gradient is attempting to increase our z value using a function of x and y, the 3D gradient is instead trying to increase the total output of f of x, y, and z. And to do that, using this visualization, we have to go away from our surface, because each surface represents a single constant value of this function. However, to increase that value, we must go away from our current surface. If you moved along the surface, this value would not change. Let's say you had x squared plus y squared plus z squared, and you simply move to the North Pole at 0, 0, 1. So you have not changed the output, which is 1. F of this value at this point is 1, which is no change from the original function. However, if we were to go to, like, say, 2, 2, 2, then it would actually be 12, which is much greater than before. And the greatest way to increase is in the direction of the normal vector to the surface. So I hope that clears everything up. And if you have any questions, please put them down in the comments. As always, thank you guys for watching, and see you guys next time.